So before I actually start my talk, let me use this awesome gathering to do some quick polls for my benefit. So how many people here actually have run Spark Streaming or are currently running Spark Streaming jobs in production? Please raise your hands. Okay, quite a few. That's good, that's good. How many people have run the network word count example? Okay, that's good, that's good. For the rest of the folks, I actually had a small introduction on what Spark Streaming is, just in case to bring everyone on the same page. So, yes, Spark Streaming, I think you've probably already heard enough in this summit, in yesterday and today, is a scalable fault-tolerant stream processing system. It can take data streams from Kafka, Flume, Kinesis, HDFS, Twitter, and then process it and write it back into file systems, databases, key value stores, push dashboards, etc. And what makes it unique is in the stream processing world is that it gives you a high-level API with joins, windows, and right out of the box, which gives almost 5 times less code than a lot of other stream processing systems. It is fault-tolerant. You get really strong exactly once and exactly one semantics out of the box, even for stateful operations. And probably the most important that makes it really unique is that it's part of this Spark ecosystem with SQL and data frames, MLlib, and so that you can intercombine streaming with all of these other parts in the ecosystem. So the way it works is that you have this thing called receivers that receive data from these various sources, Kinesis, Kafka, whatever, and chops them up into batches and pushes it into the core Spark engine. Then the Spark engine processes those batches and pushes out the results to external data stores in batches as well. And to take a very brief, quick look on how programming in it works as a starting point so that I can move on to more advanced stuff, is that first of all, you start by creating this streaming context, which is the starting point of all streaming functionality. Then using that context, you can now create what we call D streams, which is the streaming abstraction. And you can, we have these various utilities for creating D streams from Kafka, from Kinesis, etc. And then you can apply transformations on this D stream to create new D streams, very similar to RDD's transformations. And then finally, you can do more transformations to do word count and stuff on it. And then maybe what you want to do with the final result is print some of it on the screen. For that print, or you can do your own custom stuff to push it to a data store. And then all of these lines actually sets up the computation that needs to be done when the data actually comes in. To tell the system that the data, to actually start receiving and processing the data, you have to call streaming context.start. And then the whole data starts processing, starts being received and processed by the system. So let's say you have, and that is the whole program, the whole end-to-end program. So let's say you have written this program, you got it running locally, maybe you got it running on a small cluster with little bits of test data. What next? How do you take this program and to running it in production on large volumes of data on a larger cluster? That's what I'm going to talk about in this talk, and I'm going to break this thing into 3 topics. First, you need to worry about the fault tolerance and its corresponding semantics of your application. Then you need to talk about, you need to think about the performance and stability of your applications. How do you scale it out properly and stuff? And then finally, obviously, as your app is running, you need to do monitoring and think about how to upgrade the code properly in the right way and stuff. Okay, but before I jump into any of these 3 topics, we need to first understand or take a slightly deeper view of what happens under the covers of Spark Streaming. So, Spark Streaming is just like any other Spark application. There's a driver process which runs the user code, and the driver process uses a Mesos, Yarn, or Spark standalone cluster to launch a bunch of executors. And the job of the executors is to run whatever tasks that the driver asks it to run, to actually process the data or write it to some external data store, database, whatever. Spark Streaming is no different from this, except there are few more components that are specific to Spark Streaming in this infrastructure. When you run this, your Kafka word count example, corresponding to the Kafka D stream, what Spark Streaming would do is run this receiver as a long-running task. The job of the receiver is to keep receiving the data stream and divide it into blocks, and store them in the memory of the executor. What it also does is that the blocks is synchronously replicated to another executor. It's kind of an in-memory replication for fault tolerance, which I'm going to talk about next. But they are also replicated on another executor. And then periodically, every batch interval, and you can set the batch interval as part of creating the streaming context, 1 second, 2 seconds, 10 seconds, whatever you choose. Every batch interval, the driver launches tasks to run these in-memory blocks, to process them, and then finally the results are pushed out to an external data store. So this is the overview of how Spark Streaming works underneath the covers. Let's understand what happens in the case of failures and what are the semantics that you get out of this stream processing system. So why even care about failures? So if you're running a streaming applications, let's say you're doing a fraud detection on bank transactions. You definitely don't want to lose any particular transaction because of some failure that happened in the system. You want to process every transaction to make sure that all of them are not fraudulent, or otherwise you'll miss fraudulent transactions. So these sort of applications need to ensure that there is zero data loss. Every data is processed at least once in many cases. Some applications need exactly once guarantee that the data is processed exactly once and no duplicates. So there can be different kind of failures in the system, and they can be broadly categorized into driver failures and the executor failures, because those are the key components running in the system. And the system must be able to provide these guarantees despite any of these failures. And based on what are the guarantees that you need to do some additional configuration and setups in your Spark Streaming application, and that's what I'm going to talk about. So first thing, let's understand what happens if an executor fails. So let's say this is the driver that is running the streaming code. There's an executor running a receiver. If the executor running the receiver fails, then the receiver is obviously lost. All the data in the executor's memory is also lost. But this is okay, because the blocks are replicated. So what the driver will do is easily detect the failure, relaunch the receiver on a different executor, and the tasks that failed because the in-memory blocks were gone will be relaunched again on this different executor which has the duplicate blocks. So executor failures are taken care of automatically, no extra configuration needed. The more challenging part is the driver failure. So let's see what happens if the driver fails. Actually, everything is lost. All the executors are gone. All the computation that is received all the received blocks are lost. So how do you recover from that? So for that, what Spark Streaming provides is this mechanism called checkpointing, more specifically D-stream checkpointing. And what it does is that it takes this whole DAG or graph of D-streams that you have set up, all the D-stream operations, transformations, etc. All of these, this DAG of operations is taken and periodically saved to a fault-tolerant storage, HDFS, S3, etc., while the driver is active. So that if the driver fails and a new driver, you can restart the driver process using that checkpoint information inside HDFS, S3, whatever you choose. And then the restarted driver can relaunch the executors once again, relaunch the receiver, and continue processing as if nothing happened. So this is what the D-stream checkpointing allows you to do, is restart the driver and continue the computation where it had left off. To configure this, you need to do three things. One, you need to configure the driver to be restarted automatically. And I'm going to talk about it in the next slide, but all cluster managers support this. Second, you need to set a checkpoint directory in your streaming application, so which is done pretty easily. It's streaming context.checkpoint, give it the HDFS or S3 directory, and it will start using that. The third, and this is the slightly additional stuff you need to do in the code, is slightly restructure the code so that you can use checkpoints for recovery. Again, I'm going to explain that in the next few slides. So first thing, you need to configure for the driver to be automatically restarted. the Spark standalone mode, you can use Spark submit, which is the standard way of submitting your application to run in Spark. You can submit it in the cluster mode, where the driver is launched inside the cluster, and so that the cluster manager can itself monitor whether the driver is running properly or not, or it has failed. And then when you turn on the supervise mode, the driver, it will take care of actually restarting the driver if it fails. There is more information, obviously, on the online guide. For Yarn, it also supports automatic restart. You should take a look at the Yarn configuration, which specifies the number of times it will be restarted. Again, you need to launch it in the cluster mode. And for Mesos, Marathon is another system that is often used to launch jobs on Spark, and on Mesos, sorry. That also has the capability of restarting the job if it fails. So no matter what you're using, there are inbuilt support in these systems to handle driver restarts automatically. So the next part is what needs to be understood very carefully. So if you take your streaming applications, it can be broadly classified into these two parts. One is where you set up the streaming context with all the dstream operations, et cetera, all the computations that you want to do as part of your streaming applications. So there's a setup part, and then finally, once all the setup is done, there's this starting part, which says, now setup is done, start processing data. For checkpointing, you have to take all the setup and put it into this function, kind of like a factory function. What it's supposed to do is completely set up a streaming context and return that. I'm using Scala, but you can do this in Java and Python as well. And then instead of calling start directly, you have to use this pattern called streaming context get or create, and provide it two things. One is the HDFS checkpoint directory and this factory function that you have created. And the semantics of the streaming context get or create is pretty simple. What it does is that it looks up the HDFS directory that you have specified. It sees if there is checkpoint information in that it can recover from, then it will recover. If it does not find checkpoint information, basically it is being started for the first time, then it will just call the factory function to create a new context. So when you write your application using this, no matter whether your application, process is started or restarted, it can automatically figure out whether to actually start a new context or recover a past context because something had failed and it is being actually restarted. So this restructuring is important for using checkpointing. But there's another complexity, and some of you may have already noticed that after restarting, when the new executors are brought up, the data that was present in the previous executors when they failed because the driver failed, all that in-memory data that was buffered but not yet processed is lost. Obviously you don't want data to be lost, so how do you recover from that? For that, what we have introduced in Spark 1.2 is this thing called write-ahead logs. And it's similar to write-ahead logs and journals in databases and file systems. The idea is very simple. All the data that is received by the receiver and divided into blocks, all those blocks are synchronously saved to HDFS or any fault tolerant storage. So that if the driver fails and the driver is restarted, all the data can be recovered, all the blocks can be recovered from that write-ahead log, and the system can reprocess the data that was lost from the memory but recovered from the write-ahead log. And this can ensure that no data is lost. Well, to ensure that, you need to configure the write-ahead log. So, and to do that, there are 4 steps. Step 1, which you probably have already done, is enable checkpointing by setting the checkpoint directory. Then you need to explicitly enable the wall in the Spark configuration by setting this configuration parameter to true. By default, the wall is not enabled because not every streaming app requires that sort of guarantees out of the box. So it is something you need to explicitly enable. Then you need to make the receiver reliable. And out of the box, all the receivers are reliable, and by reliable, what I mean is that the receiver must acknowledge the downstream source like Kafka or Kinesis only after the data has been synchronously saved to the wall. And so that data that has been received but not saved to the wall is not act, and the data is replayed once again when the receiver comes back up after the driver recovers. And so this ensures that there is no data loss, because data will be either recovered from the wall or replayed back from the source. And finally, for efficiency, now since the data is actually being saved to the wall, which itself is replicated, you don't need to do in-memory replication. So ideally, you should turn off in-memory replication. No point replicating twice in memory and in storage. So now with this unact thing, I'll talk about semantics in the next slide. Let me touch upon another key feature that is going on underneath the covers, but I'll not elaborate on it in the interest of time, is this RDD checkpointing. So often for certain operations, especially stateful operations, you need to recover intermediate state data as well. Now, why do you need it, even though we have RDDs and RDD fault tolerance? Because if you're in stateful stream processing, the lineage of the RDDs can grow infinitely long, which is bad for fault recovery, because if you have to recover from faults, you may have to recompute all the way back to infinity, which is obviously bad for fault tolerance. So what Spark streaming automatically does is periodically save the intermediate state data to HDFS, all the actual data to the HDFS, so that at the time of recomputing on driver failure or otherwise, it can read, it limits the amount of recomputation you need to do. You can learn more about it in the programming guide, in the checkpointing section. The links are all there, so take a look when the slides get published. But let me move on to the semantics. So to understand the semantics, to ensure there is zero data loss in the whole end-to-end application, you have to make sure that every stage processes each event at least once. So now you know all the transformations that the system does are RDD transformations underneath. So that gives the same exactly once guarantee that the deterministic fault tolerant guarantees that RDD comes with in Spark. So the processing is always exactly once, as long as the received data is not lost. The outputting, so the receiving, what I've talked about till now, it gives at least one guarantee, because data may get, some of the data may get replayed from the source in more than once, duplicates. There may be duplicates. So even with checkpointing wall and reliable receivers, the semantics may be at least once. And the outputting, pushing out to the data store, it depends on the semantics that the data store provides. If you configure it right, and if you use idempotent outputs or transactional outputs, which I won't go into the details in this talk, but you can get exactly one semantics there. So in the end-to-end manner, this gives at least once end-to-end semantics. Well, that is sufficient for a lot of applications, but some applications need more. And for those applications in Spark 1.3, we have introduced the Kafka direct approach, which does not use a receiver, does not use write-ahead logs. It rather uses Kafka itself as a log. And it just treats Kafka like a file system log in a log written on a file system, and reads chunks of it right out of Kafka, pretty much like reading a file. And so you don't need to configure receivers, you don't need to configure write-ahead logs, any of that. And that gives exactly once guarantees, and which means that in the whole end-to-end pipeline, you get exactly once guarantees using this approach. There was a talk yesterday, in case you missed it, there was a talk yesterday that Cody gave, who wrote this direct Kafka approach, that you should go back and watch the YouTube video when it's published to understand more about how to achieve this exactly once guarantee. Another interesting blog post that you could take a look is by Netflix. They put Spark streaming through Chaos Monkey, which basically kills random nodes in the Spark cluster to make, and they put it Spark streaming in different configurations through this Chaos Monkey to test the resiliency of Spark streaming, and they actually found pretty interesting results that Spark streaming is fault tolerant for in all cases of executor, driver, and master standalone failures. You can take a look at that. Next, let's talk about performance stability. And for performance, I'm going to talk about the throughput. So to ensure there is a high throughput in the whole pipeline, you need to ensure there is sufficient parallelism in all the stages of the pipeline. For the receiving stage, you need to ensure that whatever source you are using, Kafka or Kinesis or others, there is sufficient number of parallelism in the source itself, like number of partitions in Kafka or number of shards in Kinesis. You need to ensure sufficient parallelism in that. And correspondingly, you also need to configure Spark streaming to receive these multiple data streams in parallel through multiple receivers. And using multiple receivers in Spark streaming is pretty easy. All you need to do is use the utility to create multiple input D streams, and then you combine those multiple input D stream into a single D stream using union, and then then you can apply all the transformations on that unified D stream. And underneath the covers, the system will receive data from multiple receivers in parallel but process them, all of them together. And it's so that's the example over there. But to ensure that you can run multiple receivers, note that these receivers are separate tasks. So to ensure multiple receivers can be run in the cluster, you need to have a sufficient number of cores. Absolute necessity is that you have at least the amount of cores as the receivers, but a good rule of thumb to ensure good performance is that the number of executors should be at least the number of receivers, so that there is one receiver running in each executor and the network bandwidth is not shared between multiple receivers. So that's a good rule of thumb to have. But note that this does not apply for the Kafka direct approach because it does not use receivers, and the Kafka direct approach takes care of parallelizing itself by doing a one-to-one partition mapping between RDDs and Kafka partitions. So there the story is much easier. In transforming, one of the key things that you need to ensure is stability of your stream processing application. And by stability, I mean the average batch processing time should be less than the batch interval. Because you need to ensure that the previous batch has been processed by the time the next batch is ready to be processed. So, to ensure that, you need to have the average batch processing time is less than the batch interval, because if you don't have that, then the batches will start getting queued up in memory. The scheduling delay for the batch will keep rising, and things will start accumulating in the memory, which is not a stable condition to be in. To achieve that, you need to reduce the batch processing time so that it's less than the batch interval. And here are like some of the steps you can do to reduce the batch processing time is that simply add more receivers. And because the nodes that run the receivers do significant amount of processing as well, because the data is stored on those machines. So a lot of the processing happens on those machines that are receiving data as well. So just increasing number of receivers further parallelizes the computation among more executors. If that is not possible because you're limited by the number of Kafka partitions, you can explicitly repartition the data into multiple partitions to further distribute in the cluster. Then if you are doing a shuffle operation like reduce by key, etc., you should specify a sufficiently large number of reducers, large number of partitions. And obviously to make all of these run in parallel, you need to get more executors and cores. Furthermore, to reduce it further, enabling cryo-serialization reduces the serialization costs quite a bit. There are online documentation on how to enable cryo-serialization. If it still doesn't work, try increasing the batch duration. Maybe you should start from, let's say, 5-second batches. If that is works well, reduce the batch or increase the batch. And then for handling data surges for which you did not plan for, you need to limit the ingestion rate of how fast the receivers will receive data by setting appropriate Spark configurations. Finally, this is also to reduce the batch size, the batch processing time. You need to ensure that you push the data, the final results out to data stores in an efficient manner. And for that, you should not use RDD for each to open up a connection and push one record at a time basically open up a connection every record. What rather you should do is use for each partition on each RDD, where you open a connection and then push out the whole connection at a time and then close the connection. That is more efficient, but what is even more efficient is that you maintain a connection pool at the executors. You just get an already open connection from the pool, use it to push the whole partition, and then return the used connection back into the pool so the other tasks can use it. This makes it very efficient to push data out into external data stores. Finally, the last but not the least, you need to monitor and upgrade your application and think about how to upgrade it. There are multiple ways you can monitor. One is the Spark Streaming UI. This is a new streaming UI that has been introduced in Spark 1.4, which shows a lot of statistics over the last 1,000 batches. You can, especially you can monitor whether the system is stable by looking at the scheduling delay, whether it is reasonably stable or not, or whether your processing time is less than the batch interval is not. And you can use the same UI to further drill down at individual batches of how long did each batch take, and within each batch, what were those actual Spark jobs that were run for each of the batches, see which is taking more amount of time, drill down into stages. You can do all of that using this UI. For long-term monitoring, what you can do is enable Ganglia or graphite metrics through by configuring the right CodaHel metrics. It's pretty easy to configure. Take a look at the link. It's all in the online guide on how to configure, configure Ganglia or graphite or your custom metric source to be used for getting long-term for operational monitoring. But for programmatic monitoring, where you want to take particular actions based on the state of the system, an interesting interface is the streaming listener, which allows you to hook into the internal events of the Spark streaming, like when batch was submitted, when batch was started, all of those internal events. You can hook into them and then take appropriate actions. You can programmatically see whether the scheduling delay is going up or not. And for inspiration, you can take a look at this class called Streaming Job Progress Listener. It's a private class, so you cannot use it directly, but you can see the source code to understand how you can calculate scheduling delays, all of that. And it's the same class that is used by the streaming UI to get all the information, so you can get the same information programmatically using the streaming listener interface. Finally, to upgrade the app, what you need to do is you can shut down gracefully, and what it ensures is that all the data that has been received is processed completely and then shut down. That ensures that no data is lost in the process of shutting down, and then you can bring back restart the application with the new code or new version of Spark, start again from where the previous application left off. You may, for Kafka, you may want to actually keep track of the offsets yourself by using the direct approach, where we expose the offsets that actually is processed within each batch. So if you want exactly one's guarantee across upgrades, you can take those offset and save it in your own data store yourself, and then when the streaming app is the updated app is started again, you can use the saved offsets to start where the previous one left off. So that gives you more exactly one's guarantee across upgrades as well. But note that if you're using checkpointing underneath, you cannot upgrade from a previous checkpoint as of yet, as of Spark 1.4. We are definitely going to work on that in the future releases. So there are a bunch of things that I would have liked to cover, but half an hour can allow me only so much. There is more information that is covered in the streaming programming guide, so go take a look. Feel free to ask me questions in the office hour later this afternoon that I have, and ask online. That's it. So thank you, everyone. I'm not sure where we have half a minute to ask questions. If there is a question that can be covered in half a minute, welcome. Yes. Is there a mic Yes.
Yep. So I have a question. So you mentioned that there's the you can shut down the context gracefully. I wonder in that case, does it like flush out all the received data and or not?
Yes, that's what graceful means, that all the received data will be processed and flushed out to the data stores, and then things will be stopped.
So in that case, the checkpoints will no longer be relevant? Like, I won't have to worry about version upgrades?
In some stateful computation cases, you may want to, the intermediate state data is stored as part of checkpoints as well. That will not be recoverable. What you could do, if you're doing a control shutdown, is save that state explicitly to an external data store, and then when the app is upgraded, pull that state explicitly back from the data store and continue from there. That can be done definitely.
I see. Thanks.
Thank you, everyone.
Oh, I have a question.
Oh.
On one of the slides, you mentioned the recovery of the failure drivers.
Yes.
And then you mentioned that it could be done by the YARN or the Mason. But I don't know what's the average recovery time for this failover.
Average recovery time, so it depends on your application. If your application has a lot of stateful data, recovery time may be slightly large because it has to recover all that state. If your application is a simple ETL kind of thing, not very stateful, recovery time is pretty fast.
Okay. So,
I think, excuse me, I'm sorry to actually interrupt. I think I'm delaying the next speaker. So can we take this question offline?
Okay.
Thank you very much.